Hello students, now we are going to start 12th unit of your crash course, which is magnetism. We know that if I current is flowing through a coil, its magnetic moment we can calculate by NIA. It means cause of current, magnetism is current. Each substance has electrons which are revolving around the nucleus in atom. Flow of electron means current. It means current is flowing in each orbit of atom. So every atom will behave like a magnet because it has magnetic moment. But why some substances are showing magnetic properties, some are not showing? To some you can make magnet and for some it is impossible to make magnet from that substance, because there are different types of materials. If in an atom number of electrons are in even, number of electron is even, it means electrons are available there in paired form. What will happen then? In a pair, both electrons are moving in opposite directions. So magnetic moment due to these both electrons are in opposite direction, so they will cancel the effect of each other. So this type of atom will not show magnetic property. These substances are known as diamagnetic substance. But if number is odd, in each atom one electron's magnetic moment is not cancelled, so it will show magnetic property that are known as para or ferro. We will discuss later. First we are going for bar magnet. We will discuss little bit about bar magnet. What is there in bar magnet? There are two poles. One is known as North Pole and one is South Pole. They are not at the end point of the magnet. They are always little bit inside. Like charge. Power of charge we denoted by Q. Power of these poles is known as pole strength and denoted by M, small m. Both poles of a bar magnet has same pole strength. Monopole is not possible in magnetism, but in electricity you can get a unit charge. Unit positive charge, unit negative charge. But in magnetism, we compare North Pole with positive charge, South Pole with negative charge. But difference is this, that monopole is not possible. Remember it. Now, what I was telling you, that in a bar magnet, these poles are not at corner of magnet. They are little bit inside. So in a magnet there are two types of lengths. One is length of bar magnet and second one is effective length of bar magnet. This effective length means distance between the two poles. Generally we are taking length of magnet means length of bar magnet, but in actual it should be distance between the poles, and it is 5/6 of total length. Like dipole moment related with magnet is known as magnetic moment, denoted by capital M, you know about it, and it is like electricity. One charge means pole strength into distance between charges means distance between poles. It is the formula for magnetic moment. On this concept, sometimes they are framing problems in competitive exams. They will say you, I have a magnet, a linear magnet whose magnetic moment was m. If I put this magnet in shape of semicircle, what is its magnetic moment now? What I told you, that magnetic moment of a magnet means pole strength into length between the poles. Suppose pole strength of this magnet was m and length was L. So magnetic moment initially it was m into L. But now distance between poles is different. It is equal to diameter. And what is L? Now it is half of circumference means pi into r. So what is radius? Radius is now L upon pi. So distance between poles means diameter means 2r. It is now 2L upon pi. So now magnetic moment should be m into, in place of L we will write 2L upon pi, new magnetic moment. But m into L, all magnetic moment, if it is m, we can write now 2m upon pi. So they can frame problem like this, like electric dipole moment. Magnetic dipole moment is also a vector quantity, means it has direction and magnitude both. Magnitude means pole strength into distance between the poles. What about direction? In electric dipole moment, I told you direction is from negative charge to positive charge. So here direction is from south pole to north pole. To north pole. It is direction of m. It is direction of m. So it is a vector quantity. If you want to add two magnetic moments, you have to take care of the directions of both magnetic moments, and you have to use vector addition formulas. Now, like electric dipole, we can calculate magnetic field in different positions. Results are same. In place of P, we will write capital M. If it is your bar magnet of pole strength M and point is on the line joining south pole and north pole, what will happen? This point is known as, there are three names. Number 1, point P, you will say with respect to this magnet, it is in Gauss A position. Number 2, you can say it is 10A position. Number 3, it is and on position. If position of point B is like this, It is on perpendicular bisector of your magnet. Distance from center, we are taking D. It is center. It is again at D distance from center. So, we will say that point P is in Gauss B position, Gauss B position. Ten B position. Or broadside on position. Three different positions, name is also there. And intensity of magnetic field, at this point, in this position, is mu naught upon 4 pi 2 m upon d cube, and at this point position intensity is mu naught upon 4 pi m upon d cube. And in general, if point is at theta angle and d distance from center, a point is at this position, general case, you can calculate intensity by the formula mu naught upon 4 pi m upon d cube under root 1 plus 3 cos square theta. Same results. But what is happening? Earth has already one magnetic field, and the south pole of Earth's magnetic field is in geographical north, not exactly in north, little bit at some angle, and south pole is towards north, north pole is towards geographical south. Its horizontal component is always in north-south direction, and its intensity is different at different places. When you are putting one magnet in 10A position or 10B position, what will happen? First we will discuss for 10A, Gauss A, axial or end-on position. Suppose it is north pole of my bar magnet and it is south pole of my bar magnet. First I am discussing at the point this. What will happen if what is the definition of intensity of magnetic field? Like electricity, like gravity, definition is same. In gravity, force experienced by unit mass is intensity of gravitational field. In electricity, force experienced by unit positive charge is intensity of electric field. In magnetism, at any point force experienced by unit north pole means a north pole whose pole strength is 1 unit is known as intensity of magnetic field. So what will happen? This north pole will repel this north pole. So direction is this. South pole will attract. So direction is this. If north pole is nearer the point, resultant intensity will go in east direction. This is east. In paper, what directions we are making? In this way. It is east, west, north, south. So if I am keeping magnets north pole or south pole in east west direction, I will not get any point where magnet's intensity of magnetic field due to this magnet can cancel the earth's magnetic field, means horizontal component of earth's magnetic field, because it is in perpendicular direction. Two vectors can cancel each other only and only if they are in opposite direction. So I will not get any point where magnet's magnetic field is cancelling the horizontal component of earth's magnetic field. That points are known as neutral point. But what will happen if now I keep my magnet like this and I am now moving from axis to this line? What will happen at this line? Again, this north pole will repel unit north pole and this south pole will attract. So resultant will be in this direction, again in east west direction. It cannot cancel this. It means if I am keeping my magnet in east west direction, to find a neutral point is impossible. Now I am keeping my magnet in this position. First I am putting north pole in the direction of north. Then I will keep south pole towards the north. What will happen? First I am seeing on this line. In this point, north pole will repel, south pole will attract. Resultant will be in this direction. Yes, just opposite to the horizontal component of Earth's magnetic field. Its direction is this, north-south. And it is that intensity of magnetic field due to this magnet. By adjusting this distance, I can change the value of B and I will get one place where they will cancel each other. So I will get one neutral point here, and with same concept one neutral point on this side. I will get neutral point. One here and with same concept one at this point. So I will get two neutral points. But if I am keeping south pole towards north, it is north direction. Now south pole is pointing north. I am assuming unit north pole at this point. This south pole will attract and this north pole will repel. So resultant is in this direction. So it cannot cancel now H because both are acting in same direction. So I will not get any neutral point. But if I am thinking about axis of magnet, means I am assuming a point at this point. What will happen at this point now? This south pole will attract and the north pole will repel, but south pole is nearer to this. So resultant force will be in the direction of south pole. So resultant magnetic field due to bar magnet is in downward direction and Earth's horizontal component is in north direction. So they can cancel each other. Means I will get one neutral point. I will get one neutral point at this point. With same concept, I will get one neutral point in this at this side. Again, I will get two neutral points. So remember, if you are keeping your magnet in east-west direction, you will get no neutral point. But if you are keeping your magnet, bar magnet, in north-south direction, you will get neutral points. If north pole is pointing north, you will get a neutral point in Gauss B position, in broadside on position, in 10B position. But if you are keeping south pole pointing north, you will get neutral points on the axis of magnet, means in 10A position, in Gauss A position, in and on position. So remember, it was an important concept. Now, like electric dipole, everywhere Earth's magnetic field is present and its horizontal component is in north-south direction pointing north, denoted by H. If I am keeping my magnet which is free to rotate here, its pole strength is M. If at this place unit pole is experiencing a force H and pole strength of my bar magnet is M, so north pole will experience a force in this direction, M into H, and south pole in opposite direction, but pole strength is same, so force is same. So what they will try? They will try to rotate the magnet. If this angle is theta, torque which are trying to rotate is one of the force into distance between both forces, means SP. So very easily we can calculate MH sin theta. If magnetic field is B, this torque you can write MB sin theta. In that place, into distance between them, yes, SP means L sin theta, sorry, it is SP is L sin theta, L. And M into L, it will become magnetic moment. So we can write M into L, capital M, MH sin theta. If field is B, you can write torque MB sin theta. If you want to keep it in this position, you have to apply this torque in opposite direction. So now you can see, if you want to rotate a magnet in magnetic field with an angle theta, you need one torque which should be MB sin theta. And work done, like electricity, we can write MB cos theta 1 minus cos theta 2. If you want to rotate magnet from theta 1 angle to theta 2 angle, you have to do work MB cos theta 1 minus theta 2. And at theta angle, potential energy is given by minus mb cos theta. It will be minimum when cos theta is maximum. So, minimum potential energy is minus mb. So, same results we have there in electricity, same here. So, you can learn easily, only you have to replace P by M, capital M, and E by B, intensity of magnetic field.